Thank you for coming. This presentation is going to be about low latency inference for your applications. So I'm Cora Iberkleid. I work for Broadcom as a developer advocate. So I'm really happy to be able to share this fun topic with you. And of course, I'm sure you've heard this already. My cards are up on the front. There are 20 cards representing our team members who are here. And if you can gather all of them, then there'll be some fun extra swag for you at the VMware booth at the end of the conference. And I think that QR code shows you all 20, so you'll know which ones you have and don't have. But these are something really fun. So as far as this topic, so I want to first set a little bit of context about inference in the modern enterprise and focus on two patterns for implementing these in production. I have a bit of a demo. We'll set up the demo, go over it, and the tech stack selected. And as you can see, spoiler alert, one of the technologies chosen for the tech stack is going to be VMware Tanzu Gemfire. And so I'll cover some capabilities that make it particularly well suited for this. So inference in the modern enterprise. There's a lot of buzz, obviously, or a lot of excitement around large language models, but there's a spectrum of AI, ML models that are used by enterprises. And so if we think about these LLMs generally, or the language or other kinds of multimodal models as larger general purpose models. They have broad capabilities. We rely on them for complex things like reasoning, things like that, and typically not trained in-house, right? We use provided ones, and versus task-specific models that are designed for very specific purposes to produce a prediction, to help with a specific decision. You can also get these pre-trained. You can obtain them from providers outside of your organization, or maybe your data science team is in the business of making these inside of your organization, right? But operationally, these are very different when you think about using these in production. The large language models are going to be a remote invocation generally. If you're hosting one, it requires special infrastructure, special GPUs, for example. And we have a very high tolerance for the latency for an LLM, right? We expect it to take seconds, minutes, whatever it takes to reason about what we're requesting, right? They're not fast operations. Whereas on the other end, with inference models, these are often embedded right into the workflow. You can run them on regular CPUs, the model itself. They tend to be much lighter weight. And we expect not just millisecond, but often microsecond latency. And these are used all kinds of use cases, right? Like things that have to do anything financial, obviously, like approving credit, or if you think about trading systems, that really gives you a sense for how quickly these have to execute. But they're also used in different industries, manufacturing, sending signals if something's failing, for example, or even just running an IoT, right? Very important to be able to react quickly if a system is about to fail or take some remedial action. But retail, healthcare as well. We've seen a use case where just flagging when even human review is needed within an automated process, right? These split-second decisions that you have to make. So there's a lot of different places where these are used. So if you think about what does it take to run an inference system in production, these would be the different pieces of the system. So of course you have your regular business logic, and then you have the actual execution of that inference prediction or decision that you're trying to make that would rely on a pre-trained inference model. And then you may or may not need to interact with additional data, either as extra input or as output, particularly as input, I guess, if we were speaking about latency here. And then often just, because we want low latency, caching is often a key component of a kind of system like this. So these are the pieces of the system that we have to work with. Now, putting these together in a way that is as quick and scalable as we need is difficult for a few different reasons, right? The performance pressures are very high, microsecond, as I mentioned, right? And they often operate under very high throughput. And so you have to be able to maintain that same latency even as you scale the system, even as with limited resources, right? So you have to be able to have a predictable latency for these applications, for these decisions. There's also pressure on the model lifecycle, right? So as these things I said are often, they're often run on regular CPUs, applications may load them into memory, so you have copies of this model in different applications or in different runtimes. So how do you manage, as an organization, the lifecycle, the distribution of those models to everywhere that they need to run? And as the model gets updated, so your data science team has an improved model, how do you make sure that that version is running on all your applications, right? So the model lifecycle management, the distribution and updates. And then finally, the data locality. If you're in a situation where your inference does need to work with additional data, especially if it's a lot of data, how do you make that work effectively as well, right? That can also be challenging, and it's both about how you architect it and also about the type of technology that you choose to support it. So I want to cover two different patterns. One, I'm going to call this edge, not necessarily IoT edge, but just edge meaning off, like not off of away from your data, and one that's requires data. So we'll call them edge and data local. So the edge inference pattern. So this is suitable when your inference does not need to access any other data. And so your inference can actually run right. So if you think about, if we're talking about Java applications, Spring Boot applications, for example, then your inference could run right in memory of your Spring application, right in the JVM. So you're co-locating the execution of the inference with the model itself, so you don't have an extra hop to get to the model, right? You're not moving data, but you still don't want that extra latency. And this is, with here, your scalability can scale with the application tier, right? So if you have a Spring Boot application running inference in memory, then you can just scale the number of Spring Boot applications, and you've scaled your inference capacity horizontally, right? So the challenge here is the model lifecycle challenge that I mentioned earlier, that if each of your applications has a copy of the model in memory, how do you make sure that they can all access the same model, and that if there's an update to the model, that they're all updated with the new model? And the second pattern we're going to look at is data local. So this is when your inference does need to access other data in order to make its prediction or its decision. And in that case, the better practice, of course, is to take the logic to the data, right? Don't move the data to the logic. You're potentially working with a lot of data. So you want not those network hops, and also not to move data over the network. So what kind of approach can you take so that you can do that and still scale the system, right? So you have like a database with one node, that probably won't scale if you're dealing with enough data. So you want to be able to scale the logic and partition the data, spread the data over multiple nodes. Usually you're talking about grids with computation layer, right? So that's the challenge there. So just kind of going a little bit deeper into these technical requirements, in order to support this idea of a model lifecycle of propagation and of models and updates, we need to have a shared storage where all applications can go to as the source of truth for the model, and also a mechanism to propagate any updates to it, right? We need a system that can support that kind of an event-driven architecture, right, of notifying and pushing models. When we talk about data-aware placement, if we have enough data that it's distributed over a grid, we need to have the intelligence to know where the data is. If it's the data that's relevant to the operation that we're executing may not be on every member of a grid. So you want to have not only the capacity to take the logic to where the data is, but to take the logic, not just the logic to the data platform, but the logic to the data members that have the data that's relevant to the logic that you're running, right? So you want to be able to do it intelligently. And then for it to be scalable in both cases. So the Spring Boot running the inference in memory is a little bit easier to reason about how that scales. You need a platform that can scale your applications effectively, but that horizontal scalability is there at the application instance level. And if you're on a data platform, you need a data platform that can keep up with you, right? That can partition and run your inference in parallel. That can split it up and run it in parallel, right? And finally, this idea of don't run an execution that you've already run, don't repeat that computation. You're going to save time, right? So for that, you need something that can also supply a cache for you. So those are our technical requirements. So I want to go through this by looking at a demo where these two patterns have been implemented. And I just want to give credit because this has been a team effort from concept to implementation to debugging. These are some of my team members here, Siva, Gregory, and Udo. And it's been fun putting this together, so I'm happy to be here to show it to you. So I'm going to just put this tech stack up front, and then we'll go into like why we're using each piece. So the one of the key pieces here is this data platform that can supply many of these things for us. So I've chosen here VMware Tanzu Gemfire, which is it was originally often described as an in-memory data grid, but I think it's exceeded the capabilities of software that's often in that category. It can function really as a transactional database as well. But it keeps data in memory, so it can persist data. It does persist data and ensure and guarantee data consistency. But the operations are done in memory, so they're very fast. So you're dealing with data very fast. It also is a grid, so it does distribute data. It has choices for how you replicate data. So if you have data, it can be on every member of the grid, or it can be on certain members. And so then it also can, it's intelligent about where it's putting things, co-locating information. So if you have order information and customer information, you need the orders for that customer to live together, right? So you can co-locate data intelligently, and so that also, as you use the compute layer on top of that, the compute is co-located with all of the data that it needs. It also can help us in the model distribution category, because Gemfire is essentially, it's a Java-based product where the information that it stores. So if you think about a databases, you have tables with columns and rows. In Gemfire, you have maps with keys and values, and the keys and the values are objects of your choice, however you design them. So it's very flexible in the terms of the kind of data you can store there. And yet it still gives us OQL as an object query language, so similar to SQL and easy syntax to understand to be able to query the data inside. Also can help us with distribution of the model. And then in terms of propagating information, it has an event, just as databases have triggers, Gemfire can generate update events that then your applications can listen for, so that they know when there's been an update to the data, in this case, the model, right? So Gemfire is actually going to serve a lot of different purposes for our use case. And importantly, it's a very, very fast product. So it's helping us also, ensure that quick latency. Yeah. It serves as a data tier, but the data that it holds can be any structure. And so in this case, we're going to put our model inside of Gemfire for storage and distribution. And then it also has a computation tier. So we're also going to run our inference. And in our second use case, when we need the inference execution to be co-located with the data, we're going to use the application tier to make sure that the inference is running at the same place as the data. So it is serving several roles, which is why it's such a good choice. Yeah. Did that answer the question? Okay, good. Okay. So that's our data platform, basically. And then for writing our application, so we're going to use Spring. We love Spring. Spring Boot gives us, production, enterprise-ready, a lot of characteristics about making applications already production grade and making development easy for developers. And Spring Data, in particular, has a project for Gemfire that's going to let us use the abstractions that Spring Data brings in order to integrate with Gemfire. So it's going to make our programming easier, basically. And then finally, because we're using a Spring Boot application, for the case where we don't need to access data, we're going to run the inference in our Spring Boot application. So we're running the inference in a JVM. And for the case where we want our inference to run with the data, we're going to run our inference on Gemfire. Gemfire is a Java-based product, also a JVM. So in both cases, we want a model that we can run inside of a JVM. And for that, there is a standard called Open Neural Network Exchange, ONNX, that packages inference models in a portable way. And then there's an ONNX runtime for Java that you can use in your Java-based code to run that model inside of your Java application. So this is going to be our way to use the same model and run it inside of the JVM in both cases. So let's go into the demo. So just to give it a little bit of a story, For the edge inference, it's a very simple, so we're focusing more on the technology, but here we're going to have our Spring Boot application basically is going to expose a controller. Through a controller, it's going to expose an endpoint that as a user, you can just send some phrase to it, right? I love spring, or this lawnmower has a great value and it's sturdy, but the color is darker than expected. Is that, what kind of comment is that? Is it positive? Is it negative? Is it, So, and then the second also, right? The lawnmower is great value, starts easily, cuts clean, but it's a bit loud. So we want to be able to know if these reviews or these comments are positive or negative. So what we're going to do is run them through a very simple sentiment model, something that downloaded from Hugging Face. And Hugging Face provides models also in ONNX format. So that was, that's just a question of getting the model in the format that you want. And it's a simple model. It just has positive or negative. So it just returns one of those two. And it turns out that the first one is positive and the second one is negative. Who knew? So, so we're always trying to optimize for performance. So here already we're seeing you want to choose the right model type, right? Choosing an LLM for this kind of use case is not the right, it's not going to give you the latency that you want, right? You need to have an inference-specific model for a sentiment model in this case, right, to do what we want. We want to minimize duplicate computation, so we're going to use, in this case, we are going to use Gemfire, but as a cache, right? Because we don't need extra data. We're just evaluating whatever the user is sending. And in order to minimize network latency, we want to co-locate the model with the inference. So we want to run the model inside of our Spring Boot application that has the controller that's going to receive the request and return to the user, right? So no other network hops. So this is how it is, right? The user sends a string. I love Spring, for example. The inference engine, we're calling it the inference engine, our Spring Boot application, is going to, when it starts up, it's going to reach out, load the model into memory. And then from then on, it can just run inference in memory, and it returns to the user. And of course, to make it faster, as it gets additional data, it'll first actually check the cache. And if it's not in the cache, then it runs the inference. If it is in the cache, it just returns the response, right? And if it's not in the cache, it does update the cache, so it's there next time. So we do have our application tier for the inference and our data tier for, here it's shown as the results cache. We're using it also for the model. So here our tech stack is our Spring Boot application with the ONNX runtime for Java libraries in our POM file, so we can do that in our app, and Gemfire for the caching in the model. There we go, oh, this one. Okay, so we're also using Gemfire here. So here we have another component within our Spring Boot application that when it starts up, it checks, we actually have the files that are downloaded from Hugging Face are just on disk. So this component is going to check disk, read those models, and then put them in Gemfire. So that's basically the data science team saying, here's a model, and you have an application that writes that to Gemfire, so now everybody can share it. But this model loader is also going to keep polling that directory. So if the data science team puts an updated model in that directory, then this model loader is going to re-upload that into Gemfire. Gemfire has the capability, as I mentioned, of sending events upon change. And so it's going to produce a change event. The application has a listener. And so the application will be notified, and it will refresh its in-memory ONNX runtime session with the new model. So that's what this is showing, right? So if that tech stack is still the application is Spring Boot with Spring Data for Gemfire in order to interact with the model store. And again, we're still leveraging Gemfire because Gemfire has that capability as well of change events. So I will run that for you. And so here's our application. And this is, so I'll show you really quickly. Let's walk through this setup. I'm going to mix a little bit of the second use case with the first one, I think, because it's all kind of together in code. So this is one repo. It's on GitHub on the address that was on the slide, the acknowledgement slide. And it basically, when you build this application, it'll build all three. This is the Spring Boot app that we've been talking about so far that has both the part that does the inference in memory for the Spring Boot app. It also has the model loader built into it. I guess these are really two concerns. You might do them separately, but they're two modules within the same Spring Boot application using Spring Modulith, which is a really cool project. different topic, but just a way to organize the logical components of your code within your code base. And then it builds. This is going to be the jar file that we're going to use to run in Gemfire in a few minutes when we do use case 2. But this jar, it's also a jar file that's built here. And then they share some domain objects. They both read the model from the model region on Gemfire. The region is the equivalent of a table, the map that stores data in Gemfire. So they both read the model from there, and they both cache the sentiment there. So there's some shared domain objects that we're using. So that's in a different jar file that they can both load. So basically, building this application will build those 3 jar files. And also, this application, the inference app. So we're showcasing a little bit of Spring Modulith, as I said, for these 3 different modules here. But we're also, so here's the model loader. Here's the in-memory inference. We're also showcasing here some Spring Boot support for Docker Compose. So when this application starts up, it's also going to run this Docker Compose file. And this Docker Compose file is going to run in Docker here, Gemfire. So it's going to start, so Gemfire is a grid, so it has a locator member, and then all of the members that are actually storing data and doing the computation. And so it's going to start, I'm just going to start a 1 server. So it'll be one locator and one member in the grid. And then also we want to create it's kind of the equivalent of your create table. So we're going to do a create region for the region that's going to store the model, the region that's going to cache the results for inference, and eventually the region for the extra data for. It's a couple of years at least. Yeah. And in the Docker Compose file, so we have some additional sections in the Docker Compose file that will call scripts or execute code to do the region creation. And also for use case 2, we're going to want to deploy that jar file that's going to do the inference on the data platform. So that's all kind of baked into the Docker Compose file, and we're giving Spring Boot the ability to do the Docker Compose up, Docker Compose down. So all we have to do is, and I've already downloaded the model files from Hugging Face are here. So the model is essentially the model file, and then the tokenizer that helps sort of, treat the data so that it can be submitted to the model. So these 2 files constitute the model artifacts. So I'm going to start this ops scripts. Yes. It's been a little while, 3. Okay. So we're going to build and deploy. Oh, yeah, sorry. Why is it? One second. Just get all this right. So, okay, so we're going to run this. So basically, this is just going to build all 3 jar files and start up the application one. And this application one is going to do everything that we want. It's going to download our images, start our Docker containers for the locator and the member, and then connect to them to create the 3 regions. So here's under here, Gemfire, we have our Docker Compose file here. Let me make this a little bit smaller. So it's just going through the Compose file, right? So it says, okay, first start the Gemfire locator. The second one is it does a little bit of configuration. It starts the Gemfire server after that. And then because we had these 2 things enabled through the profiles, right? In the application properties, we said, do these 2 profiles, the region init and the function deploy. So it's also going to do the region init, which is going to run this script, create 3 regions. One is going to store our model, one is going to cache our sentiment results, and one is going to be the product reviews, which we need for case 2. And it's going to deploy the jar file for the function. And that code is just here. So just as it deploys it, gives it to the locator puts it on every member of the cluster. So after that, the application will finish starting up, and it will also send a test. It sends a test sentiment. So we can see that here. It sends a message called, it just says, woohoo, everything's working well. If this is sent, everything's working well, which forces the application to go to Gemfire, pull the model into memory, run the inference in memory, and put something into cache. So we've done that at least once. We know if all of this started right. And we can check that here. Let me just get the command to start this, to check this. Where is it? Here, I can run this command. Oh, sorry. It's docker exec. Okay, so we're going to connect to the Gemfire locator, or we get into the container that has it. Then we connect to the locator, and then we can run commands. So we can do, like, for example, list regions. So it's created the 3 regions that we want, and it's already deployed the function that we're going to need for case 2, which is called count positive review. So it gives that function a name. We've indicated in our when we register it, we want it to have this ID. That's going to be important when we want to call this. And as I mentioned, there's also this object query language that you can use. That, for example, if we do a select, let's see, select. Let's see, what are we going to run? Let's select everything from the sentiment results. Maybe I can do it this way, it's easier. So what's been cached so far? So far, we've only run 1 sentiment. So we've cached as the key, we have the actual sentiment. So if somebody sends this sentiment again, we're just going to return positive. We don't actually have to run the inference, right? And the AI model is stored as as binaries. So the key is sentiment, and the value is, I'll show you how we know that. In our libraries, our shared domain, oops. Our AI model data type has 2 byte arrays, one for the ONNX file and one for the JSON tokenizer file. So again, you can store any kind of data in Gemfire, so very powerful. Okay, so now that we've got that running, we can run a test function. So I'll do this twice for you. So ops, scripts. Oh, which one was this? Edge request. So this is 4, 0, 4. Okay, so the reason I'm running it from here instead of just there is a Swagger UI, but I want to run it this way because I just have a little function here to measure how long the request took. But we're just really just sending to this endpoint localhost 8080 to the app AI inference check sentiment. We're sending the I love spring string and expecting it to respond, right? So it's done that in 0.0744 seconds. So I'm going to run it again. And now it's an order of magnitude faster, right? So that's the difference. Thank you. So that's the difference, the cache. So, I mean, this is already, this is my machine. It's not a particularly new machine. I know it feels slower today than other days as well, but this is already fast because this is already running the inference in the JVM, right? There was no other hop to get this done. And it's already a model that is fast, right? This is the difference. This is with a hop because it's going into Gemfire in the Docker container, but this is the power of an in-memory cache, right? So it's not just it's not an on-disk. It's not only that we're not running the inference again, but we're also not doing a disk read. So that's another part of the power of Gemfire. Okay, so then the other thing I want to show you here is the updating the model. So if the data science team makes any change to the JSON file or to the ONNX file, we have our model loader component that's been polling the directory where those models are found. And so the way I'm going to fake this is by just adding a line at the end of the file so that the update time on the file changes. And the way that we're going to verify that it worked is we're going to look at the log file for the application. Right now, it just did our last I love spring over here. We sent it I love spring. It said that it was positive. So now I'm going to change the model. And we'll just go back to the log file of the application. So the application has a listener that comes from the Spring Data for Gemfire project. that is listening for this change event that's emitted by Gemfire. And so you can see here that it has detected an event, and so it's updated the local ONNX session. It's the same model, so there's no change in behavior. But I could optionally, if I wanted to, I didn't, but I could optionally expire the cache, for example, right? If I decide this is a new model, so all old results are not relevant anymore, then I could do something like that as well. But essentially, the Spring Boot, so any number of instances of Spring Boot applications that I have, by virtue of changing the model, updating in Gemfire, all of them have gotten an event to go and refresh their runtime with the new model. So okay, so that's use case one. And we can, we could walk through the code, but I think maybe I could just get to the presentation first and make sure we cover everything. So, what's wrong? Okay, so where were we? Edge inference demo in action, right? So, well, I can show you. I took some screenshots of the code, so I can show you that. So basically, this is, again, so just the project. We have the 3 jar files. We have our Docker Compose setup. This is the model loader. So here's the, as I mentioned, the data type for storing the AI model with the 2 byte arrays. And we have our application module initializer, which when this application starts up, it's going to run this code, call the initialize method, down here, which uses this Gemfire template from Spring Data for Gemfire project to very easily, with very little code, write this information to the model. And here's our key sentiment, the string sentiment. Then we have here our engine module, which is, and I'm using the word module because it comes from the concept of Spring Modulith. It's just the way that I've organized the code in the application. So this is the one that exposes the endpoint and returns negative or positive, takes the result of the model, which is a number, and maps it to either negative or positive. And it's implementing you can see it extends this abstract common event processing cache listener. So you can see there that it's going to, there's like an update, there's a method here, process entry event. That's what it's using when it gets the model updates to refresh the runtime. And otherwise, it sets up the session, so it does all sort of the ONNX runtime for Java configuration, and finally the execute, where you actually send I love Spring, and it executes that against the model that it has in memory. So that's all part of the engine module. Okay, so that's use case 1, all right? Now, what if your inference requires access to additional data? Then you don't want to run the inference inside of your Spring Boot app. You want to run the inference on your data platform, in this case on Gemfire. And as I mentioned, Gemfire is basically a JVM-based project, so you can a product, so you can run Java code there. So in this case, our story is going to be that as a user now, instead of sending a phrase, I would just send a product, like lawnmower. And so this goes to our Spring Boot app that's acting as our controller layer. And instead of running the inference, this is going to trigger a function that we've deployed onto Gemfire, and the inference is happening inside the function in Gemfire. So now the function in Gemfire, a little piece of Java code running in Gemfire, is going to do something similar. It's going to go get the model from that same AI model region, load it, run the, it can also access the additional, so it knows lawnmower, so it has to go to the table of products and say, for lawnmower, give me all of the reviews for lawnmower. For each review, it's going to do the inference. It'll check the cache first, so it doesn't duplicate computations. And if that review has not been evaluated yet, it will evaluate the sentiment for that review. It'll count the positive ones, and then it'll send the results to the piece of code that the Spring Boot app that the user connected with, which is the one that invoked the function. Now, if you imagine that this is all happening on a grid, and we have our product reviews data maybe located on half of the members of that grid, then what Gemfire would do is it would trigger the function on all of the members of the grid that have product review data. And so we're counting positive reviews for lawnmowers, and let's say there's 5 on each of the 10 members of the grid. So there's 50 of them, but each one is only counting 5. So each one sends their partial results back to the invoker of the function, our Spring Boot app that the user connected to that invoked the function. And so that has a collector, an aggregator. So it adds them all up, and then it says we have 50 positive reviews, right? So this is the MapReduce paradigm or the scatter-gather paradigm, right? So again, another reason that Gemfire is so useful, because it gives us that capability. So that is our second use case. So here we're seeing, in terms of the paradigms for optimizing performance, in addition to the ones that we already saw in case 1, we also have moving the computation to the data layer, which we're doing by running this function in Gemfire. We're favoring in-memory data access. So we could be doing this with a data platform that does disk access, but we don't want that, right? We want something that's not only the cache for the sentiment results, no disk access. So it's going to have also our product reviews in memory, right? So even the data access for the extra data that we need is going to be fast. And it's going to, because it has this ability to not only partition the data across the grid, but also trigger the function on the members of the grid that have relevant data, it's going to parallelize the computation on the members where the relevant data is sitting, right? So we get all of that. So the way it looks is we have our product reviews aggregator, another module in that same, put everything in the same Spring Boot app. Maybe not the best practice, but that's what I did here. So that's just another top-level directory in the application for product reviews. This one, it does 2 things. So when it loads up, it actually takes a CSV file where I have all the product reviews, and it puts them into a region that we're calling product reviews. But that's our big data store, right? So let's say all Amazon reviews are there, for example, and you want to check the reviews for a certain product. So we're just using it for the demo to populate that. But the real workflow here is that a user sends something like lawnmower, the product reviews aggregator with its Spring data for Gemfire, its easy ability to interact with Gemfire will trigger the function telling it which region to operate on. So it's going to say, run this count positive reviews function on the product reviews region. And so then Gemfire will make sure to trigger the function everywhere that there are product reviews. And then that function has to load the model and get every review from the reviews region. And for every review, check the cache. If it's not in the cache, run the inference and save it to cache, and then return the results to the product reviews aggregator, which is going to collect all the partial results from all of the members, although we only have 1 here, add them all up, and then give the final result to the user, right? So that's the architecture. So we've co-located the model with the inference and the data, even across the distributed platform, right? And keeping this in-memory capability so that it's fast. So, and again, we can run, it's because we're taking advantage of this portable model protocol, what's the word? Packaging, the ONNX, and the ability to run it in Java, we can use the same model, right? So our model distribution and propagation solution works for this also, because we've chosen to use model packaging that is compatible with Java runtime, and both of these are Java runtime. Okay, cool. So let me show that to you working first, and then we'll come back here. So we've, yeah, let me run it, I guess. So change events, so test the function. Okay, so we saw that the function was there, right? We did a list functions here, and it's called count positive reviews. So we can just run. So here I think it should be maybe 5. No, 6. Let's try 6. No, okay, it's got to be 7 then. Okay, send function requests. Oh, and this is sort of similar. I guess I'll open it. Similar to the other one where I'm doing it from the script because, again, I just want to time it. But all we're doing is sending the word, asking for product reviews and for lawnmowers. That's it. Nothing fancy there. So we're going to do that. So now we've invoked the function on the I can show you the log here. Show logs member equals server 1, and I think can do lines equals 100. So this is the log file on the server. So we should see that the function was invoked. So yeah, so our data has duplicates in it because I'm not that creative. But so what we should see is that it's going to count 11 positive reviews because there's 20-some reviews there's 21 reviews for lawnmower, and there are 11 positive ones. But because they're duplicated, we won't see that many in the cache, as we shouldn't. Here we go. There's actually only like 3 unique ones. But many people can say I love spring, and those are many people saying that it's positive. So we want to count them individually, but the cache, this sort of shows, right, that the cache is going to help you not do repeated computation. And so, so we saw the log file, we saw the change events, and then we saw the function, and if we run it again, so that took 1.6 seconds. Again, not the most powerful machine. Gemfire's fast, but Gemfire in Docker on my old laptop, maybe not so much. But hitting cache is 0.017. So big difference there, right? So back to this. Yeah. Oh, because it's, okay, so in the first use case, I sent a string, just I love spring. And it went to the Spring Boot app, and the Spring Boot app did the inference in memory, and it returned the result to me. In the second use case, I sent the word lawnmowers to the app. The app triggered the function running in Gemfire and sent the word lawnmowers to the function. The function went to the product reviews table, selected all of the reviews for lawnmower. It got 21 out. For each one of the 21, it computed because we didn't have any cached, right? So it computed 21 times it didn't compute it like 3 or 4 times, right? Because it cached them. But it's still, for each one of them, it either computed the inference or it went to cache and got the result. And then it sent back the result to the app that it just added that. I mean, there was only one thing to add, and it returned it. But it did basically multiple more operations than the first one, right? Yeah, because it also selected all the data, went through each one. Yeah, so it's a much more rich sort of workflow. Yeah. So in this case, we have so this is the product reviews module. So this is still in our Spring Boot app. This is the one that's exposing the controller to the user so that we can send lawnmower, and it's going to return lawnmower with the count of the 11 positives. And I think I did maybe just glossed over that, but that's right here. ID is lawnmower, positive counts 11, right? That's the response that we're getting in the return type for the client-facing function. And here we see that it's using Spring Framework data Gemfire function, the @filter annotation down here, and the on-region annotations here. And so it's just showing like how Spring data for Gemfire really makes it easy to achieve this pretty sophisticated interaction with Gemfire where you're invoking a function on this particular region with ease, right?
Can you do like Spring data repository?
Yes, yeah, yep. And so this is our count, and here, so this is the function. So this is the code, part of the code, that is packaged as a separate jar and deployed to Gemfire, running. So this is what we've invoked, running in Gemfire. And so this is a Java function, and I can highlight here. So it does the actual execution. It does the same. It uses the same. It's not all shown here. I guess what I wanted to show here was this: the ID. The ID is count positive reviews. So when I do list functions, this is where it gets the name of the function, and in here, count positive reviews. So the method name matches the function name, and so Spring kind of magically, Gemfire and Spring marry those two together. So that's all you have to do for it to invoke the right function on the right region, right? So it's not that much coding. but pretty powerful. So we did the demo in action. Okay, so just to recap, right? So we're using Gemfire here as a model distribution engine and propagation of changes, as a low latency database, right? Because it's storing all this data, but it's also making it available to us as in-memory operations rather than disk I/O. But it's also a low latency database because it does also offer that persistence layer with guaranteed consistency. So we get sort of the best with both worlds there. It's a scalable, as a grid, right, with data aware, with a compute platform, so we can bring our computation to the cluster and make sure that it runs exactly where the data is, co-locate related data if necessary, and as a shared cache for our applications. We're using Spring Boot and Spring Data for Gemfire because all coding is better and easier with Spring, and Spring for Data for Gemfire makes integrating with Gemfire easier. And then ONNX was that sort of that final key to be able to take a model and run it in the JVM and take advantage of the fact that Gemfire also runs, is a JVM, so it just simplified things even more. So just to highlight, right, we look at the two patterns, look at these technologies. The Gemfire is fast, reliable, and it's got some extra optimizations as well. So I think I've got 10 more minutes. So I don't always get to this part of the presentation, but since we're here, and we have 10 minutes, I just wanted to highlight. So Gemfire is a really, I think it's an amazing product, and there's more to it, obviously, than what I'm going to talk about in the next few slides. But I kind of selected some of the features that I think are most relevant to this use case. This is actually more representative of, like, people often use Gemfire for this use case rather than the use case that I just presented, which is just, if you're trying to access data from your application and it's slowing down, it's not meeting your SLAs, but your app is not the bottleneck. It's actually the data platform is not fast or scalable enough or fast at scale as you need. And so you have to think about the actual data platform has to scale to your needs. And so that's where Gemfire often is introduced into architectures to improve latency, which is why I wanted to approach it a little bit by this other angle, because there's other ways that Gemfire can be used, but this is sort of the classic one. And so as you've seen already, right? So Gemfire introduces this distributed data layer. But it's truly an in-memory database, not just I guess data grid sort of implies more just cache, but it is a data grid, and it gives you this predictable low latency, right? It'll scale in a way that your latency you'll be able to count on it, but it also supports real-time transactional workloads because of its ability to it's favoring for consistency. So it's not just cache or horizontal scale, but actual transactions. And there's even enterprises that have used this as their system of.
You guys open sourced it a few years ago, right?
It was open source but not anymore.
Right. It was the team at VMware was doing all the contributions, and they're like, yeah, we're doing the open source, but we were getting no feedback, so it was like, we're taking extra steps to open source, and bring it back.
Okay.
So yeah.
So this distributed key value regions, right? So it's kind of like a map, a Java map with like a superpowered Java map, I would say. So the key and the values can be any Java object that you like. It's very efficient in terms of serialization and deserialization. It has a portable data exchange format of its own that enables it. So it can deserialize and deserialize directly into Java objects, but also it has this PDX format that allows it to be interoperable with other client languages. So it's not only for Java client use cases. You can use it with other languages. And this PDX format also enables really fast searching. So for example, if it's searching for data, it doesn't have to deserialize data in order to select records. So if you have a Java object as a value that has an ID, a customer, a description, and you want to select by customer, let's say it has name and description, you want to select by name, it doesn't have to deserialize all the data in order to do that selection by name of the data. So it's a really efficient that's all these reasons why Gemfire is fast. Right, and it's so distributed. Here, the scaling. So when you put data, so for example, here showing a 3-member cluster. In each case, you can choose how your data is replicated, right? So you can either have your data in what's called a replicated region. So all of your data will be on every member of the cluster. So your client can talk to any one of them. It will be equally fast on a read. Or you can choose to have your data, maybe you don't want to write your data maybe 100 times. You only need 2 or 3 replications, so you can choose what's called a partitioned region. So your data will be replicated on just a few members. And in that case, one is designated as primary and the others are secondary. If a member goes down or becomes unavailable, Gemfire has a protocol. It has sort of a gossip circle amongst members. So if one of the members goes down, eventually they will notice, and there's a whole protocol of electing one to evaluate whether or not that one has to be taken out or not. And if it reaches the thresholds, then it's fenced off and not used anymore. And the remaining ones also, there's also a protocol by which they decide to re-replicate the data to meet the number of replications that you wanted. But because this system works well, because often if you try to have a system that has full consistency, you often give up on a little bit of latency. And so Gemfire wants to, as much as possible, optimize both. But it wants to optimize for latency, but it also wants to offer the consistency. So this is what enables it to offer the consistency without sacrificing the latency. They're always monitoring each other, and if anything goes wrong, they react effectively and efficiently. This co-location, I mentioned this earlier, right? It's not just about taking, in our demo example, there's only product reviews. So it is great to take the function to where the product review data is, but if you also have product review data and you need that inference operation to also access customer data. You want to know which customers reviewed the product. Maybe you want those two things together. And so in partitioning the data across nodes, Gemfire can also be intelligent about keeping the data together. So the reviews by this set of customers can live with that customer information, for example, or orders, as in this example. The server-side functions, right? The ability to deploy functions and run them where the data is, and the ability to have these executed in parallel. And this we saw in the demo. The function runs on the platform, returns the count to the piece of code that invoked the function, and that one will aggregate all the results, whatever that aggregation looks like, right? We added them. It's not always adding, but you decide that based on your use case. And then we saw this in the updates. So this continuous query event delivery. So whenever there's a change of data, Gemfire can emit a change event, whether it's different kinds of, it could be an update, it could be a create, whatever. And then from your application, you can listen for those and take action accordingly. And so, yeah, so it's designed, it's a again, shared nothing architecture. These members are not sharing any infrastructure with each other, so they don't slow each other down. They don't cause shared failures. The scaling of the cluster can be dynamic. Again, it takes care of rebalancing. Just as when a node falls out of service, it rebalances data. If you want to add a node, or if you're adding back a node that had failed, it will rebalance data. Because of this, you can also do rolling upgrades without any downtime. And there's also an intelligence built in on the client side, either anything from the clients maintaining a cache, so they don't even have to go to the Gemfire server. They can and Gemfire, it's also if that cache needs to be expired, then Gemfire can also work with the client to say this data has to be expired. You have to build your own cache, but there are ways to maintain a client-side copy of the cache. Or the clients knowing also kind of where the data that they need is. So there's an intelligence built in on the client side. And then in terms of how you run it, so obviously I've been running it here in Docker, but you can run it on bare metal, you can run it on sort of VM level automation with a Kubernetes operator, or our favorite way is on Tanzu platform, which every level up you go reduces the amount of operations that you need to do, obviously. So bare metal, VM level automation, Kubernetes. And then the Tanzu platform will give you the highest level because it not only automates the operational side, but it also provides a developer self-service aspect. So, so you can just say, I need a Gemfire cluster, and then the platform will just give it to you and inject the credentials into your application. So I guess key takeaways is that real-time inference is often embedded right into our workflow, so it's very, very close to our code as developers. And so I just wanted to show you two different patterns that you can consider in terms of trying to reduce the latency in these workflows, and that in order to achieve the best scenario for latency, to minimize your latency, to take into account not just architectural decisions on the application side, but also these important decisions about what kind of technology that you're providing on the data side, because it will make a very big difference, right, in enabling you to take advantage of more features in your architecture and in actually giving you the response time that you need to meet those SLAs. So I find that this is a very practical stack for this, especially if you're already in the Spring ecosystem and in the Java ecosystem. So Spring Boot, Spring Data for Gemfire, and this ONNX, this ONNX protocol is kind of like that missing link to bring it all together. And so, yeah, that's what I have for you today. Thank you. Cool. Yeah.
Quick question. As far as I understand, like in the beginning you mentioned that there are two types of models, like big ones and smaller ones for fintech, healthcare, etc. Like this is where your target is. Like you want to put like those smaller models inside of application, right? Like, but is there any limits on the size of those models in terms of I don't know what, like the number of parameters or like resource consumption? Because there is no way it does not consume extra memory, CPU, etc. There must be some impact, right, on the application.
Yeah, I can't give you a number on that, but yeah, there's a point at which you may be working with models that are not, that either for whatever reason maybe cannot be, I don't know why they wouldn't be, but like why maybe you can't turn them into ONNX format, or so then maybe they're not compatible in your JVM. And yeah, there's a point at which you can only hold so much in the JVM, but you can scale vertically. You'd have to scale your JVM vertically first. So yeah, when you reach the limit of scaling vertically for any reason, hardware or, then yeah, that's the same things would apply. Yeah, not infinite, I guess.
So then the suggestion is like, as you mentioned, like this ONNX format model, like this is where...
yeah. The ONNX will just allow you to run the model inside of your JVM. And then as long as your hardware allows for it, you scale the JVM vertically for a larger model. And then I guess if that becomes your limitation, if your model is truly too big to run inside your JVM on your hardware, then you can run the model on at that point you would need a model server. You could run the model on more powerful hardware. And then you have that single network hop. But yeah, as long as you can scale the JVM vertically enough to run the model, then these two things will be relevant. These two architectures will be relevant. Yeah. Yeah. Sorry. Yeah. One question back there, and then yeah. Oh, you're just pointing. Okay.
About a question. For example, a small language model with like 250 million parameters. Do you think it can handle it?
I haven't tested the limits of it. This one is megabytes, the one that I use, 700 megabytes. So I haven't tested the limits of what size of model you would be able to hold in the JVM. Yeah. Do you have a better answer for that? Yeah. A little harder depending.
One of the JVMs can have like hundreds of gigabytes of heat, right?
Yeah. So there you go. As long as your hardware can sustain it. Yeah.
I may get a little bit of GC for this one,
Not going to go to 25.
Yeah, Java's also getting much more efficient, right? So maybe that helps. But these are, yeah. But this is, I don't know if those, what the impact of those improvements are on this, but yeah, I don't have a number for what the limit would be on a JVM for vertical scaling. Yeah.
Any issues with native?
I haven't tried this with native, but is there any reason
We could do it
it wouldn't work?
off Gemfire, we could do it as a native, and yeah, we could still load the.
Why wouldn't it work? Yeah.
As a native image.
Yeah, I don't know why it
We
wouldn't
don't
work.
do that, but the native image won't run inside of Gemfire.
Yeah. But there's nothing like extra dynamic that it requires. So yeah, you should be able to. Yeah.
Yeah. How easy is it to set up? Do you just have to pull down the containers and run it?
For this setup, yeah, it's very easy. I mean, I started it. Yeah, when you saw me run the package, Maven package in Java jar, it set everything up. It downloaded the Gemfire Docker image from Docker Hub, I guess, is it? Yeah. So it started the containers and it ran a couple of scripts to create the regions. I have it's all it's in the demo, so you can here. The demo's on GitHub. So let me just go back to the here. Yeah, so it's C Iberkleid, low latency AI. Everything is there. So I'm going to clean up the README a little bit because right now it says that you have to run a Gemfire script before I switched it to Docker Compose in the Spring Boot app. So I'll update the README so it's all correct. But yeah, it was literally, you saw me start from absolute scratch. Yeah.
Only on Spring, can you use Focus or Micronaut?
I guess you could. I mean, so I'm using Spring Data for Gemfire to facilitate the interaction with Gemfire. So you probably end up writing more code. Yeah. Cool. Well, get a card before you go. Thank you for coming. Thank you so much.